Okay, so it is time. We are going to start on the week 7, which focuses on recurrent neural networks, and subsequently the blocks of the recurrent neural network are replaced with LSTM and GRU. So comparison between these three, why and where these are to be used, and then application. One application we have discovered here, that is. So the application is into video understanding using CNN and RNN. Okay, so that is what we are going to do. Is it visible? Yes, it is visible. Okay. Okay. And audible as well. Okay. So first we are going to go through some lecture slides to fresh things up. Okay. I'm going to explain few of the things as well. Then we move on to some question practice, and if time remains, I'm going to show something on the assignment as well. Is the assignment that is there is a coding type this time. Okay, so we're going to see that as well. Okay, so let's get started now. And so as you can see, the assignment is a coding type assignment. So first of all, we are going to check the video lectures here. No, not the video lectures, the lecture material. Let's see how many we've been able to download here. One, three. Okay, two and four are left. So the introduction of the today's week starts with that our fully connected neural networks and convolutional neural network only take fixed size input and give fixed size output. If we need some variable size input and variable size output, then what are we going to do on that? So that is the problem we have. Okay, uh, suppose we're inputting a sentence. Okay, so sentence can have different lengths, and the output suppose maybe a machine translation that will also can have different lengths. Okay, so how do we tackle that problem? Okay, so it is an NLP problem, but NLP is not our focus here. Okay, but just to give an example. Okay, so we'll get on the lecture slides now to understand better. Okay, so some questions, these are not important maybe for today's thing. Oh, okay. So the size of the input is always fixed, as you can see. So we are encountering a sequence learning problem. So suppose there is a temporal data set and we need to learn the sequence sequence, how the data is coming one after another, is what our problem entails now. So here, this is the previous example we had. We're using convolutional network, always of the fixed size, okay, and so these are the problems that we're trying to address. Suppose sentence completion, the input sentence uh, may be of different size, and output sentence, output completed one, may also be of different size, okay. That is the problem we have here. So these are not fixed, as you can see. So this is how they so what we are shown here is that there are few computational blocks here, okay, three there, okay, and output is one, so we're giving one as input and getting one as output, okay, and we're giving one as input, one data as input, but we're getting many output. The length is 3 here, okay. So similarly 3, many to 1, many to many, many to and many to many 2 times, okay. Example they have given. So some of the examples are, suppose for many to 1 is the text summarize, is suppose the sentiment analysis. Suppose you're giving a sentence, whether it is a sad, the sentiment is sad or happy or something else, okay. So sentence can be of different length, so many, and one is the, what is the sentiment, so that is a one word answer, right. So that is of many to one variety. One to many, suppose you're given a image and you need to generate the caption, so that is one to many, okay. So and the one to one can be like that, you're given an image, and what is the content of the image, suppose like just you have to do classification work, okay. So that is one to one, okay. And so this is what we have here. So this is what we have here. And many to many is also there, okay. Many to many is the image machine translation, okay, of any translation of a language, okay. And many so another example is video classification frame level, okay. So you're given the video, so at frame wise you're given as the input, and what does the each frame contains is like, so so the one to one problem has been done many times, okay. So suppose in the one to one problem, let me write it down. So in the one to one problem, you inserted one image and you got the class here, okay. Here what you're doing, you're inputting a video. What it means is a frame, each frame. So each frame is an image, okay. You're given images like this, and you get the class like this, okay. So this is a many to many problem. Any doubt up to this point? Okay. So continuing. So here the RNN is introduced, how RNN works. So what happens is that, so you are inputting X, okay, into the this neural network block. The output is fed again to the RNN, okay. It continues and until at last the Y is outputted, okay. So the important thing is that RNN has an internal state that is updated as the sequence is processed, okay. So with time the RNN's internal state is updated, so that is how it learns. So you can so that was like, you can unfold the operation how it happens. So the RNN is only one block here, okay. but so it is shown multiple times to just show the recurrence, actually one after another, how steps are happening. So you input the x here, okay, you get some y, but there is also hidden state h here, h0 say. So that is updated to h1 here, so that is the hidden state here. Then again x2 is given, y2 output you get, and again the hidden state updated to h3, h2, okay. So like that it goes on, okay. And hidden state is continuously updated with every input, every step, okay. Not every input, means the x may not be feed again and again, but the hidden state would be also still be updated. Any doubt? This is how there is also mathematical formulation, okay. So the state is ht, it is defined, okay. So the function here, whatever function that is, okay, takes xt and ht minus 1, okay. So xt is the input at the time t, okay, and ht minus 1 is the hidden state at the previous time step, okay. So it takes both of these and updates the new hidden state, okay. And with the hidden state you can also find yt, okay. So it is defined as another function, suppose f something, okay, f ab, and not ab, suppose fa, and you feed the ht here, okay. So and also some to for some you need also learnable parameter here, okay. So for that, suppose you have another c here, okay. C is the matrix which has the learnable parameters, okay. So this is how it is. So then you can get the yt at different steps as well. That would be shown here as well. So this is the network, as you can see. This is ht here, and this is what they use. So one example of this function, fuw, is tan hyperbolic they're using, okay. And as you can see, this is the matrix associated with xt, learnable matrix, learnable weight matrix. W is another like that, okay. And here there is the v, which I had written as c. Any doubt up to this point? This is how they define it, okay. Any doubt? No doubt, right? Okay. Moving on. So move on to a concept called computational graph, which will help us to write the uh, help us to write the relation between these different equations in a more appropriate way, more understandable way, through which you can compute the gradients and prepare the backpropagation algorithm. So that is why it is important. So a lot of things are written that these are not important. Yes. Too many slides. Okay. So we are going to the main point we have here. Is that this is how it is represented. So so what you can see in this. So these are the some of the uh, these are you are doing, okay, these operations. So b is given by a plus z, a is given by x multiplied y, and c is torch sum of b, okay. So as you can see, torch sum when you're doing, what means is that b is a vector. If b is a vector, then a and z are also vector, okay. And something like that, okay. And x and y, whatever the dimension, it is not clear that way, okay. But you can see, so to get c you are using the summation operation here, okay, dot sum, that is written here. Next what you get is so b is the input, c is the output, the operation is this summation, okay. Next uh, b is the output, as you can see, the input is a and z here, and the operation is sum, so that has been written here. Subsequently, x and y are the input, the product is this operation, you get the a, okay. So that has been written. Is that clear? So this operation, as you can express, is in this form, okay. Easier to express this way, okay. So you can do this for this one as well. Okay, so what you're going to do here is that W is write it down. So W is inputted here, X is also input. Okay, this is a function which does what? It takes the product of two operation. Okay, so it means that f a b is equals to a multiplied b. Okay, and so this is the output you get. Okay, let me write down the output here. Okay, now you have the input b here. Okay, these two are input into another function f a b. Let's write it something else. Okay, x comma y, let's say, so x plus y. Okay, so this becomes wx plus b. Okay, further what you get is this is feed into f c, which is equals to tan hyperbolic c. So this outputs the tan hyperbolic of whatever is the input. Okay, so this is the output, then becomes tan wx plus b. Okay, and this is represented as this f of this is equals to h. Okay, it's becoming a little dirty, yeah, but and h is the input into h is the input. Okay, v is also the input. Okay, h and v are input into what? Another function, suppose mn is equals to m into n. Okay, this hv is the output. Okay, another way this a comes here and this comes as well. These are summed into vh plus a, and this is equals to y. So that's how it is written. Okay, it will be dirty here, but clear way they have written as well. Okay, so as you can see how it is written. Okay, so this way you can get the answer. Further, this is the fuw function. Okay, so where did you first see the fuw? You see it here. Okay, fuw. Okay, so u and w are the parameters here. Okay, so they write the parameters at the bottom now. Okay, so the parameter, what means the parameters are u and w here. Okay, so with that you can write it easily that fuw is the function. Okay, u goes with x1 and w goes with h0. Okay, the output is the updated state h1. Okay, that's how you have to write it. So they have written subsequently. Okay, like that. So we're using the same weight matrix at each time step. Okay, so that makes it easier. Now for the y you have to write as well. Okay, so y you can write as well. So y, suppose time t is equals to what is going to be, v was the weight matrix here, multiplied h1. Okay, and this is put into another function. Okay, which is the usually the softmax one. Okay, so whatever be the function here. Okay, the parameter is v तो f भी लिखते हैं. So and this is the loss from each one. So what they are doing is the correct one. Suppose the predicted one is the cap. Okay, predicted usually is represented by cap here. So y1 minus y cap is the loss. Okay, so this is L1. Okay, so like that L2, L3, L4, LT. Okay, so like that you sum this up into the total loss L. Okay, understood up to this point? Because we need to find the loss to back propagate the loss. Okay, and for that we need to calculate the required gradients as well with respect to all the parameters. Any doubt? No doubt, right? Okay, moving on. So there are many formats, okay? So all these y, x may not be there depending on the construct of the problem. If it is a many to one problem, you're giving many x input here, but the output is only one here, okay? Suppose the sentiment, okay? So that is how it is. So you don't calculate the y at each step, only at the last step, okay? And so so here you can see the difference between these two graphs, these two charts are that you are taking this one, okay? So y here means that f, suppose v is the parameter and v into ht. So this is the only y equation you have here, okay? But here what you're seeing that you're taking the multiple each of them, okay? So what it means is that y is dependent on each of the h here, okay? And this h1 h2 dot ht, okay? Suppose I make a vector in this representation, this multiplied with v here, okay? Because you have to keep the parameter same, okay? And this is the function f, parameter v. This is some of the output. So what is it is taking understanding from all the h, which is usually not required most of the situation, okay? You can just do it from the last one. Another one is this, where there is only one input x, okay? But you get the different outputs at each step, okay? So yt can be written as f of v. So what is there? V is there and ht, okay? This is our output here. Clear? Any doubt up to this point? So you are seeing the different problems 1 to 1, 1 to many, many to 1 right now within this pictographical form. So now 1 to many is there, okay? So what they have done, so 1 is the input here and the many output, okay? So if you put 0 here, what does it mean? It is deterministic, so it will just, so it will negate the, suppose you have to write h2 here, what is going to be f, uw is there, but only w will act. You will be multiplied with x, which is 0, so only this, okay? And you get what? W into h1, like that, h2 h3, like that. Further, so another thing they can do is 1 to many, they input the output of the previous recurrence, okay? The y1 is input into this, okay? Dimensions have to be appropriate because like they are one means the x and y has to be the same dimension, okay? Otherwise it will not be possible. So there is one example here, okay? Character level language model. So in language model, what happens? We predict words, word tokens, but here the token is of the characters, one letter, okay? So this is a lower level problem, okay? Easier to solve, okay? So what they have done? They have done a one hot encoded form. So what it means is that one at the top, others are 0, so only h is there, okay? That is what it means. If e is there, then 0 1 0 0, like that. If L is there, then 0 0 1 0. Okay? This is a hidden that hidden h1. Okay, these are the weight of h. Uh, the H at different steps, suppose HT. Okay. These are the Y values. Okay. Only one value here. Okay. And they softmax that, and they take the highest probabilities, which is this. Okay. So it means E, right? So the second value is the highest probability, so it is E. And the output layer, what does that one means? So as you can see, it may mean HT here. Okay. Okay. Further, let's go here. Now this can be fed back here. Okay. Acha. So the output layer I have to see. Okay. These are not so important, so let's move on. So they can output the input the output again. Okay, and then read it again. Okay, so this is how it's done. Okay, so this is what we are done with. Now this is the one, then 2 is there. So we will do this after taking a little bit of break. Okay, and then we'll do some questions as well. So here the second lecture is on how to back propagate the gradients in the RNN. Okay, RNN, recurrent neural network, are very like bad reputation for vanishing gradient problem and exploding gradient as well. Okay, it really is a very problematic scene here, and so that is what we are here. Okay, so even the so that is what we will see. So and also what happens in longer RNN sequence, there is forgetfulness. Okay, so the further hidden representation does not remember the full context, it keeps forgetting. So that's why some memory component was needed, and that is why the LSTM was introduced by Smith Hoover. Okay, that is what you can see. So just a little break, then continue the LSTM and GRU, then the application of that into whatever that was. Okay, so let's continue. Okay, number of people has increased. It is good to take break. As soon as I joined, Swati has left. Okay. So we will look at the back propagation part now. Okay, and so these are the exact two equations we are using. Okay, and so this is the weight, okay, associated with hidden state, which is recurrently used. Okay, the same weight is again and again used, and V is the for generating the Y at that state. Okay, U is associated with X. Okay, wherever the X is input is given, it is used. Okay, and the same is used, and there is like no change in the there is no like sudden change. There may be so that these weights may be changed during back propagation, but during forward pass these are not changed. Okay, so the loss function is what we see here. Okay, so this is the cross entropy loss. So let me explain that. Okay, so cross entropy loss is this. This is the original. Okay, so cross entropy loss is exclusively used for classification. Okay, so YT represents uh, that the original class that it should be. Okay, and what has been predicted. Okay, okay, so that is the cross entropy loss. Okay, the product of that is cross entropy loss. And now you can understand for each time t there is a this one. Okay, so what it means is that for each time t your y1 y2 yt is there. So you're calculating loss cross entropy loss at each of them, then summing those over t. Okay, then the minus is always there in cross entropy loss. Okay, okay, clear. So that is how it is. Okay, there can be more depth into what is cross entropy loss, why is it like that, but we're not going to go on that. So this is the thing. So first the softmax function is applied. Okay, you get the yt, and then this loss function. Okay, further as you can see, these are the error. Okay, so what it means that y1 minus y1 cap. Okay, this is the error. No, this is the sorry, this is the so error and loss are the same thing. So which is mean what it means is this is the this one y0 log of y0 cap minus. Okay, so this is the error here. Okay, and these are added. Okay, so that what it becomes over t time t minus is in the front yt log of yt cap. Correct. So back propagation is also written that way. Okay, back propagation over weight w here. Okay, so weight is w is associated with the hidden state h. Okay, so that one. Okay, so that is equals to sum over like this. Okay, further so this is what we're going to calculate here. Okay, so let me write the equation first here. Okay, or maybe here. Okay, so this is what they're getting. How they're getting, let me show you. Okay, so they are only picked up E3. So what it means that they have given that del E by del V can be written as summation over T del E T by del V. Okay, So now you can just pick one and see how it works. Okay, so now E3 is given as, I think the highest attendance is today. So E3 is given as YT, Y3, Y3, and minus of is always there, Y3 cap. Okay, so this is the one. Okay, and now this is given in our data set. Okay, this Y3 is the original value. Okay, what is going to be, and suppose in that character language model, as you remember, suppose this is E. Okay, okay, like that, and so that is it. Okay, and this is the prediction of what it's going to be. So this is the one hot encoded, suppose 0 1 0 0. So this is the vector you have. Okay, and this is like something like 0.001, 0.8, 0.2, and something like that. Okay, 0.1918, 0.1001. Okay, so this is the, so you can understand this one. Okay, so that E, you remember in that character language model, that was okay. So one hot encoded vector. Okay, so E was in the second value, so that is 1, and others are 0. And this is the prediction we have got. Okay, so as you can understand, this one will be changing throughout the training of the model. Okay, so you can take derivative with respect to it because it is changing. Okay, and this will lead to the loss also changing with respect to it. Okay, so del E by del Y3 cap, we've done this. Okay, now Y3 is dependent. Okay, Y3 cap, so Y3 cap is now we are focusing on. So first of all, you should remember that we need the loss and gradient with respect to V, because V is the parameter we have here. Okay, parameter matrix we have, and but to get to that we need to have a chain rule. Okay, so that we can compute. Okay, so first this is what we need here. So this can be written as this, because the loss is directly dependent on Y3 cap. You can see this one, right? Now the Y3 cap is dependent on Z. How? Y3 cap is equals to soft max with respect to, they have defined Z3 here. Here Z3 is equals to VH3. Okay, so this is dependent on Z3 for sure. Okay, that can be written as with chain rule as del Y cap del Z3 del Z3 del V. Now Z3 is dependent on V. Okay, so this way you can first calculate the gradient of Z3 with respect to V, then this one, and then this one, then multiply them all together. Okay, now del Z3 by del V is H3, right? Okay, okay, here we are. So this is equals to H here, H3. Okay, okay, next what we have here is Y3, and now this one. Okay, now this is the cross entropy we have. Okay, minus Y3 log Y3 cap. Okay, and this is equals to E3. Now take derivative with respect to Y3 cap. Del by del Y3 cap. Okay, so hard to write here. So this becomes minus Y3 1 by Y3 cap. Okay, so that is minus Y by 3 by Y3 cap. Okay, so let me write the answer here, minus Y3 by Y3 cap, multiplied by del Y3 by Z3. Now let me do it here. Okay, so Y3 is defined as a soft max, which is summation over T e to the power ZT and e to the power Z3. correct? Now I need derivative with respect to y3 respect to z del z3, right? Z3 z3. What is this going to be? So this is going to be so this divide rule, okay? So first you take derivative with respect to z3, which is e to the power z3, okay? And now you leave this alone, e to the power zt minus, don't take derivative of this, take derivative of zt e to the power zt with respect to z3. Okay, so how it is going to happen? Suppose z, when you're taking the derivative, so I'm going to great details for it, okay? Okay, is everybody able to understand? What we're going through now? So the back propagation sequence, how it comes, that is what I'm currently looking at. Okay, any doubt? Okay, so z, with respect to z3 I'm taking the derivative, okay? And here okay, so what is this? This is sum over z1 z2 plus like that zn zt capital T. So when I'm with respect to z3 I'm doing others are will be equal to 0, okay? You understand, right? Del z1 by z3 will be 0 because z1 is not dependent on z3, only z3 one will be left, okay? So e z3 is there and summation over t e to the power zt square of this. Okay, so if you subtract this one, what you get? This becomes y3 minus y3 square, okay? y3 1 minus y3, okay? Is it y3 or y3 cap, right? This is cut, okay? This comes out to be, well, there are two cases actually. What happens is that when you're taking derivative with respect to z3, once it is z, okay, this is what it comes out to be, and the output, the outer product is because so this will be like y minus y cap minus y into h transpose, okay? So this is how it is, okay? So h vector you and you multiply it with each of them, okay? That is how you get, okay? Now the w part, it was the w part, now v part. Okay, the w part you can write is like this, okay? h3 is already also dependent on w, so from that we get, okay? And so here here what we'll get, H2 will be there, right? So as you can see here, H3 is dependent on H2, and H2 we also don't know. Okay, so what will this one? Okay, del H3 by del W will become, what will it become? Del W is H2, right? No. First the tan part will be there, but after that, uh, what was I saying? So with respect to it, when you take the derivative with respect to del W, what will happen with respect to W? So first the tan part will be there, according to that, back, what do you call, chain rule, and then you finally get the H2 at the end as well. Okay, because uh, because um, because due to chain rule, what will happen that when you take the derivative of WH2 with respect to W, you get H2 here. So so that is explained here. Okay, now H2 is also dependent on again on W, so that has to be chain rule again and again. So this becomes summation. Okay, summation of this form. Okay, so that is the, when you do it with respect to W. And now with respect to U. Okay, so if recurrently X is input, then you'll get the same, a similar one. So they have also simplified this one. Del H3 by H1 can be written as this. Okay, so you get this one. Okay, means like if you go here, this H3 by HK is there term. Okay, so you simplify this to, okay, this can be written as this. Okay, so you can get this product form here. The W is there, W you have done, and for similarly you can do it for X, for U. Okay, so because it is recurrently dependent, so the summation part comes as well. You should check out this derivation with yourself as well. Okay, these are very helpful. These are like popular interview questions. Okay, and how to get the gradient descent from in recurrent neural network. Okay, so further, uh, moving on, we'll take the this one. So what happens, as I said, in RNN, what happens that at higher, as the age moves higher, the index moves higher, it forgets the previous context.
Hello, sir. I have a question on the previous slide.
Okay.
The equation that you showed, no, this BPTT.
Hmm.
Yeah. Is there any reason that we have structured? This equation is structured in this way, or is there any particular?
Let's go here. Okay. So as you see, till this del H3 by del W we have to calculate. Okay, and so this is the form we have. Okay, so if we have to do del H3 by del W here, so this this W is there, but this H2 is also dependent on W. Okay, you understand?
Okay.
So when we are doing del H3 by del W, what it means is that so there are two dependent variables here. Okay, which depends uh, on W. Okay, so it is similar to this. Suppose so you have tan x and sin x here. Okay, and I need derivative with respect to no, suppose it is x sin x. Okay, I need derivative with respect to x here. Quite similar to this, right? Some function of this. Okay, so I need the derivative of this function with respect to x. Understood? So what am I going to do? First, I'm going to take the derivative of uh, okay, just yeah. So so you can understand. So this is a similar problem, right? This is a function of x sin x. Okay. So this w is the x here, and h2 is corresponds to sin x. Okay, which is dependent on x, and this is a function. Okay, the function is the tan hyperbolic here. Okay, and the output is something uh, whom I need to take the derivative of. Okay, so how we do this one? So first, the function is directly related with this one. Okay, so first we take derivative with respect to x sin x of f. Understood? Then we take the derivative of x sin x with respect to whatever that is inside. Okay. Okay. So we are going to do this, right? And so this is a product rule. Okay. So what it gives here? So it will be derivative of x with respect to x into sin x plus derivative x into derivative of sin x with respect to x, similar to like this. Okay, so that is how we are going to do here. Okay, so h3 with respect to w, what it means is that first we're going to do del h3 by by uh, by del of this. Okay, but these are not varying. Okay, so w h2, this is what we'll get. Then del of w h2 by del of w. Okay, now so del of w h2. Okay, so first, so what we get here, this del of w becomes so you can do you have to use the product rule, right? So what is going to be del of w by w becomes 1, so del of, so and so that is 1. Okay, and we are left with h2, right? h2 plus what we get here, del of uh, w times del of h2 by del w. Okay, this is the plus form we get. So let me take a clearer page. Okay, otherwise confusion will be there. So what equation we had here? So first of all, what we had was del e3 by del w, we have to find out. Okay, and that is equals to e3 by y3 cap, y3 cap by h3, h3 by del w. y3 cap del y3 cap del, what was it, del h3, h3, del h3 by del w. Okay, now going to do this one, del h3 by del w. Okay, so what we see here, that h3 is equals to function of u into x plus w h2. Okay, now we found out that this has to be del h3 by derivative with respect to this. Okay, but here we are not changing with respect to u or x at that time. So x is a constant, is input, but we are not changing with respect to u that time. Okay, so that is going to be del w h2. Okay, now we have to do del w h2 with respect to del w. This problem we have, using product rule, what we get, first take derivative with respect to w. Okay, so we are left with h2 here, then uh, keep leave h2 w alone and take derivative h2 with respect to w. So this, from here you get the summation structure. Okay, and okay, or you can write this one as uh, what have they written here, so this is there. Okay, and okay, where did we reach here? Let's write it down. Okay, so next page, going to the next page, maybe I can smaller this one. Okay, so what we are left here, del e3 by del y3 cap and del y3 cap by del h3 into, and also this one is there, del h3 by del w h2, h2 plus w del h2 by del w. Okay, okay, now if you see here, so this part is there, this part is there. Okay, the variation is here only. Okay, so you are taking so these are divided into two parts. Okay, so let's focus on the h3 part. How are you going to write the h3 part here? Del y3 cap, del y3 cap, del h3, okay, del h3, del h 3 is there. Okay, so that will be cancelled. Okay, if k is equals to 3, that is what we're focusing on, del h3 by del w. Okay, so for h3, for a k equals to 3, you get this one. So getting h2 here, we're getting here. So there is a k equals to 3, right? And this is h3 del w del h3 by del w. Let's see. Also getting this h2 here. Acha acha. So but this h2 has to be taken out as well. So then you'll get the equation. Okay, but you can understand that you're getting the summation structure from using the product rule actually. Okay,
Okay. Yeah.
so if you would do it again, then you'll get h1 and then h0, then there will be no dependence left. So then you'll get four terms, okay, of this structure. Okay, and then so we're getting the structure from the product. Okay, and so we are done with this one. Where was I was here. Okay, and I was done, okay, and next moving to so what happens that when you go higher there, the age that hidden representation does not remember the earlier context. Okay, so that is why it was the LSTM was introduced. So for more context, what they did, means we're moving towards the LSTM. We have not reached LSTM here. So this is how we're moving to LSTM. So on time t, so they are in LSTM there is not only the hidden state ht, there is also a cell state ct. Okay, so this stores the long term information, as you say. So you can see this. Okay, so there are three gates which decide erase, whether to erase, write or read. On each times to each element of the gates can be opened, closed or somewhere in between. Okay, gates are dynamic, the value is computed. Okay, so you can see this one. Okay, LSTM, the structure is like this. All RNNs are the form of chain of repeating modules, okay, of neural network. Repeating modules in the vanilla RNN is a single layer with 10 activation. Okay, so there's a single layer of neural network, but in case of LSTM it is far more complicated. So you have xt minus 1, which is the input. Okay, there is a block here. Okay, you get ht minus 1. uh, no, this is the simple one, I think. This is the LSTM. Okay, now so you are inputting xt here. Okay, so there is a so something coming from here. Okay, let's see the equation here. It's a very hazy one. So ht minus 1, ct minus 1 coming from the previous block. Okay, and then the different things happening, and you're getting ct and ht. Okay, so a lot of things are happening. Okay, so ht minus 1 and xt minus 1, some this function f is applied, it is applied, ct cap is applied, ct is applied, lot of things. Okay, uh, so this is what is done. So this is the cell state, how it is happening. Okay, so this is a simplified one. This is the gate there. Okay, and this is sigma here. Sigma neural network point-wise multiplication operation. So this point-wise multiplication operation is there. This is what that is representing, and so there is sigmoid based neural network output, and you get multiplied with point-wise with ct minus 1, then add with something else here coming from here with 10 hyperbolic, and then you add that, and so it's a complicated operation actually, as you can see. So this is what they have done for get. Okay, so from this you can, these are the important outputs here. So input get decide what information to throw away from the cell state, cell content, new content is written, cell state, some is forgotten. Okay, this is how the cell state is updated, and this is how it is done. Okay, so just to summarize here, as you can see, gate controls what is kept versus forgotten from the previous cell state. Okay. Input gate controls the part of the new cell state are returned to the cell. Okay. And output gate control what part of the cells are output to the hidden state. Okay. New cell content. This is the new content to be returned to the cell. Okay, these are the things. So it solves the vanishing gradient problem as well. So these are not so important actually. Now moving on to gated recurrent unit. It's a simpler alternative to LSTM. It combines forget input gate into single update gate. Okay, and cell state and hidden states are merged. Okay, this is the structure you have. So update gate control what part of the hidden state preserved or updated. Reset gate controls what part of the previous are used to compute new content. So GRU you can use for speed, for faster learning and fewer parameters. Okay, these are the things here. Okay, so we are done. So further, but we can move to the questions now. And what's the time now? 6:13. Okay, so moving to the questions here now. So what are these? We have to match these. Okay, so many to one. Okay, so many input but one output. So that is sentiment classification, right? Simple enough. Why is this not working? And this is not a PDF. It's just saying that's why. So let's open this in a presentation form. Okay, this is the one. So, okay, yeah. So many to one classification. So you're getting many input. That is, suppose a sentence. So it is many words, and the output is what is the sentiment in the sentence. So that is many to one. This is matched. Okay. Many to many machine translation. One to many music generation. Suppose you gave some singer's name, and then you have to generate the music. Okay, clear? Right? Any doubt? Further, so these are the given one. What are the problems in traditional RNNs? Prone to vanishing and exploding gradient. This is another problem. Processing the data sequentially. All of these are problem. Okay. But LSTM or GRU does not solve the sequential data learning problem. Okay, they also learn sequentially only. Okay, the so the sequentially learning problem. Okay, so what happens in sequential learning? You cannot parallelize the you cannot parallelize. Okay, you're learning one at a time. If you can learn on all of them, all of the hidden representation at once, then it is a faster method. Then you can put each of the learning process into different computing system, and you can lead it can lead to faster conversions. Okay, and that is exactly done with transformer architecture, which learns all at once, all of the hidden representation at once, and feed them into, and the learning is done in the GPU. Okay, so that is how it is parallelized. Okay, output to the next hidden state. Which one is this one? It is the forget, na? Acha. So this is the matching output to the next hidden state. Okay, how much should be stored, and what new information should be stored is B. This is the another one. Okay, this is the matching done. 1C, like that. What are the key structural and gating mechanism difference between the LSTM and GRU? So GRUs have how many gates? Two gates. Okay, LSTM has this one. Clear? Memory cell is LSTM, both have separate memory cell. Both are separate, right? Acha, into the hidden state. If you see the lectures, you can. Gating mechanism. LSTM is an update gate and a reset gate, while GRUs use a input gate and an output gate. Now LSTM use three gates: input, forward, output, GRU update and reset gate. Okay, the 3C. Acha, 3B. B is the one. Acha, B is the one. Complexity. GRU more computation expensive than LSTM because they have more gates. That's wrong. B is the correct one. 4B. Done. Next. Which of the matrices are responsible for vanishing and exploding gradient in RNN? So this is the one. Okay, because it is repeated recurrently. Okay, that's why it is the problem. So consider RNN to be trained on a sequence data using backpropagation through time. Given the recurrent matrix with eigenvalues greater than 1. Okay. What are the potential issues might arise during the training process? So exploding gradient might happen because it will get multiplied one again and again. So if it is any number is greater than 1, that is multiplied again and again, it becomes very large with sequential multiplication. The answer is 2. Right? Any doubt? Good representation today. Okay, we'll go back to the final application based. Okay, so video understanding. Using CNN and RNN, the 3D convolutions are there, 2D convolutions. Time is another dimension. Time is a separate entity. Okay, like this. Frame 1, frame 2. So these are the input of several seven what you say timed images there. Okay, or frames. Okay, and hardwired. Okay, what is hardwired here? I don't know too much here. What is hardwired? Then convolution is done, subsampling, those things. Okay, what you have already seen. Okay, the dimensionality keeps reducing. Okay, finally convolution again, and fully controlled network and inference. Okay, using 2D CNN, input video single frame convolutions, spatial stream coordinate, multiple frame optical flow. Okay, these are the things they have done. So on the visual features, they're using CNN, and then sequential learning using LSTM and prediction. So for each image frame, they are using this learning method. Okay, and CNN, then LSTM, then you can make prediction. Okay, for each frame. So several things what action recognition can be done, what the person is in the image is doing. Okay, so what other can be done? Action forecasting, object tracking, dynamic scene understanding, and temporal action segmentation. These are the things that can be done. Okay, any doubt? This was the application. I did not get into the depth of it. Okay, acha, there is another is the assignment that you have. Okay, so I will stop presenting from the iPad and present from the my own screen. Okay, now I'm going to present from the computer here. You can see, right? uh, okay, and we move to the assignment here. My screen visible, right?
Yes.
So this is the Jupyter notebook they have. The solution is also there. So you don't have to. This is the imports and calls here. There's one image that you are reading here. calculate the height and width of the image, convert the into a numpy array, initialize okay, code start here, fine. Define a function to populate the row sum array. Acha. Those are the from the previous week, I think, because these things we had done in the previous week here. Yeah, from the previous week it is, okay. The region sum and those things, okay. So just you use the equations in the previous week, you will be able to do that, and some other questions as well here. Multitask loss. So they mismatched this one, yeah. It's not week 7 problems actually. Boundary box and everything. Dice loss implementation. The dice loss is the type of loss you can see from the Google and implement accordingly. Acha, here the LSTM comes, okay. Training and test data set they have to prepare, so you are getting training and test data set from here, okay. Now you can use an LSTM here. This is a LSTL class, you can form an object from this, okay. So these have to be done. So my reference will be uh, this is the one. There was a GitHub one, you can find the detail here. Do it like that. Hard to find now. Maybe YouTube it was. Okay, this is the one. Okay, you can take help from this one, okay, this video, then you can do it, okay. Not very hard, okay. See how it is done. See some more questions here. Here training here. Rest of the thing will be easy, just see the video by Aladdin Person. He has a GitHub link as well, just find that out as well. Yes, this one. Not sure, maybe not this one. Just take any online reference, and if you're unable to, I'll clear it up in the next week. Okay. I think this is the video I'd used because it's already seen here. Okay. Any other thing here? Okay. This is also one. That should be the one. Yeah. Okay. So I'm going to stop it now. Any doubt? Okay, I'm going to stop it here. Okay. Thank you very much. In doubt?